Welcome to the Baker Center. We have a distinguished visitor today. We'll get to him in a moment, but I want to do a little advertising and marketing for the Baker Center. For those of you that aren't familiar with what we do, we are now 11 years old as a center. Our facility is now 6 years old. We have undergraduate student enrichment programs. We work with political science and the delivery of their master's program in public policy and administration. We are growing a research portfolio in the areas of energy policy, environmental policy, and global security. And we support a very active lecture series from seminars like this that just kind of percolate up to some of our high-level lectures, if I will, that include the Baker Distinguished Lecture that we hosted most recently, Tom Brokaw. So today we have the distinct pleasure of welcoming Sam Weaver, Dr. Sam Weaver from Proton Power Incorporated, and I'll read this so that I don't make any mistakes in my introduction of Dr. Weaver. Dr. Weaver and his colleague Dan Hensley have developed a new renewable energy system for producing low-cost hydrogen from biomass and waste resources. The technology is referred to as cellulose to hydrogen power and is carbon negative. I think it's particularly noteworthy that Dr. Weaver and Dan have worked together for over 40 years. That's what I heard today at lunch. Most marriages don't last for 40 years, so I think it's really remarkable that entrepreneurs are able to stick together for that long of a period of time. Dr. Weaver is an entrepreneur. He has more than 40 years of experience founding and operating over a dozen companies in the automotive, aerospace, advanced materials, and energy fields. His recent focus has been on renewable green energy production at Proton Power Incorporated. And Cool Energy, Inc., and that's located in Colorado, Dr. Weaver, a waste-to-heat electricity producer. Dr. Weaver has 11 patents and was made a fellow of ASTM when he received their prestigious Award of Merit. Founded in 2005, Proton Power Incorporated currently has 82 employees, as well as a strong physical presence in East Tennessee with more than 85,000 square feet of manufacturing and office space. Please help me give Dr. Weaver a warm welcome to the Baker Center.
You'd think an engineer could figure these things out, wouldn't you? Okay, this is kind of, we kind of kept a low profile for the last several years, and this is kind of our coming out video.
Imagine a whole new way of thinking about energy. One that is both cooperative and competitive, renewable and plentiful, and doesn't require incentives to be cost-effective. Imagine a future with abundant energy for all of mankind. One where sources of energy don't compete with food. Limited natural resources are preserved, and everyone on our planet is able to live to their full potential. Imagine a green technology that doesn't come with any caveats. One that is scalable and on demand, clean and carbon negative, and provides energy in all the forms we need it. Imagine harnessing the lightest and most abundant element in the universe. One that will never have a shortage, never pollute the air or our water, and is renewable in every sense of the word. Imagine a world where we're able to choose among the energy resources, not between them. Imagine powering a sustainable, clean tomorrow, not just here, but across the globe. Imagine Proton Power.
So, my favorite philosopher, Yogi Berra, once said, The future ain't what it used to be. And you know, he's exactly right, because we are consuming our fossil fuels at a prodigious rate. And if we're going to have energy in our future, and we better have energy in our future, then we have to find some technologies that are going to give us a renewable, sustainable approach to the problem. And what better way to do that than to have technologies that are cost-effective and competitive with fossil fuels. And perhaps if we can do that, then we can find ways in which we can produce some renewable technologies, competitive technologies, before we run out of fossil fuels. But it's going to be a problem because we're using those fossil fuels at an ever-increasing rate and an ever-increasing cost. And to make that transition is going to be difficult. So what do we do at Proton Power? Well, what we do is we make cheap hydrogen from biomass, and we make it on demand. And from that, we can create energy all the ways we use it: heat, electricity, and liquid fuel. And by biomass, we mean any kind of plant-based material like the tree out there. And I'm going to discuss a little bit about the process that we go through. But before we do that, I'm going to talk to you about what I'm going to talk to you about. First, while you're still awake, we're going to talk about the technology. Then we're going to talk about the benefits. We're going to talk a little bit about Proton Power, who we are. We're going to talk about how we're different, and the example I'm going to use is what we're doing with liquid fuel. And I'm going to give you a little history where we came from, about why we're different. And then we're going to talk about what's the point of all this. What is the worldview of where we're headed? And this is a notional diagram of how the system works. We take any kind of feedstock that is biomass-based or plant-based, really any kind of carbon, hydrogen, oxygen molecule, including 6 of the 7 plastics. We actually prefer to recycle as much of the plastics as you can, but if you can't recycle it anymore, we can use that in our system as well. We put it through our what we call our chip unit, our cellulose to hydrogen power, and from that we generate heat, electricity, and liquid fuel. And we have 2 co-products along with this. One of them is water, and the other is biochar. In the case of water, the sort of metric here is that for every ton of biomass you put in, you get a half a ton of water. In East Tennessee, it rains all the time. We don't need that water, but there are places like Arizona that appreciate that water a lot. And then biochar has all the minerals that the plant took out of the ground, so it's a great soil supplement. And it has about 85 to 90% carbon. And so when you put that in the ground for your soil supplement, we end up with a carbon negative product. The way to think about it is the plant, as it grows, it takes CO2 and water out of the air, a little bit of energy from the sun. We put it through our process, and we reverse that. We add a little bit of energy, we create hydrogen. When the hydrogen burns, it becomes water. And we release some CO2, but we don't release as much CO2 back into the air as the plant took out because we have the carbon in the biochar. So, what are the general advantages? Well, according to the Energy Information Agency, if we can get feedstock for $40 a ton, we can be the low-cost supplier of electricity, cheaper than combined cycle natural gas. It eliminates the need for a hydrogen distribution system and eliminates the need for hydrogen storage systems. Those are the 3 big issues relative to having a hydrogen economy. And the American Hydrogen Association says that it'll take between now and 2050 and $50 billion to solve these problems. Well, we weren't smart enough to solve 2 and 3, so we just eliminated it, made it a hydrogen on demand. Another thing that's important about the technology is the systems are scalable. And when we say scalable, that means we can go from small to large systems, in principle, all the way from home use to multi-megawatt. The cellulose fuel is renewable. Byproduct is water. Much of the fuel can be waste products. And the process is carbon negative. And as I said before, we can use this technology to create energy all the ways we use it: heat, electricity, and liquid fuel. So what are some of the ways we can do that? Well, we can take the synthetic gas that we generate, our hydrogen-rich gas stream, and put it through electrical generators. We can take municipal solid waste, and the guys with the landfill are really happy because now they have a new revenue stream, reduces what goes in their landfill by 96%, so extends the life of the landfill by 25 times. And the biochar, because of the high surface area, it captures any toxic materials that you have from like pressure-treated wood, so those toxic materials won't leach into the groundwater. You can use the hydrogen to run a fuel cell. In fact, we have a program now with a company in California to do that. The thing we like about it is both systems are totally quiet and they have low maintenance. And as we said before, we can use this biomass to make liquid fuel. So this is a notional diagram about how the system works. We take the biomass that comes in and we chop it up to about 1/4 of an inch. We run it through our gasifier. And from the gasifier, we put it into a buffer so we can control precisely the amount of gas that goes into the generator to generate the electricity. Our first commercial install here is at Wampler Farm Sausage. And for entrepreneurs, you know, your first adopters are your heroes. And the Wampler farm system, particularly Teddy Wampler, is our hero. He's the guy that you saw in the blue jeans with his hands on his hip. This is a 0.5 megawatt nameplate, 500 kilowatts. To give you a little perspective, that's enough to run about 250 homes. We actually have a megawatt, 1,000 kilowatts worth of power in that system, both from the generators and from our chip units. And you could actually expand this to about 3 times that size on that same footprint if you're so inclined. Now, this is a picture into this, and in the upper left-hand corner, that's where the biomass comes in, and it's chopped up as it comes in to somewhere in the 3 to 6 inch range. And then that drag rake pulls it up into a channel, and over in the channel it goes down into what's called a hammer mill, and that breaks it up into the 1/4 inch size. And from there up into that storage area, the bin there holds about 8 hours worth of biomass. From there it gets augered into our gasifiers, and from the gasifiers into the generators. And now I'm going to give you a little motion to all those words. I think I am. That's the drag rake pulling the biomass up in the channel. Then it goes down into the hammer mill and breaks it up into 1/4 inch into our gasifiers. These are operating at about 1,000 degrees centigrade, about 1,800 Fahrenheit. Here we're pulling out the biochar, double slide gate valve, so we make sure air doesn't get back into the system. And we flare the gas before we run it into the generators to make sure we have a steady stream. And then we start the... We start those generators up right off of our chip gas. We don't have to use any other gas to start it up. Talk a little bit about that gas stream. We have about a 65% hydrogen in our gas stream, a typical syngas, because a lot of other people make synthetic gases. A typical one is about 15%. As a result of that, we got about a 50% higher energy content in our gas stream. And the reason that's important is because with the higher energy content, you can make more efficient use of your generators and get a little bit more electricity out of it. Some of the operational advantages of the system. If we're making electricity, we don't have to dry the feedstock if it's less than 45% moisture. That's important for a lot of applications around the world. We're also flexible to many different feedstocks, and the reason being flexible to different feedstocks is important is if your feedstock supplier decides they want to up the price and you don't like it, you can go to a different feedstock. In fact, you can change this feedstock on the fly if you want to do that. It's a one-step, single-step process for electrical production, and we like to use the Einstein principle, make it as simple as possible, but no simpler. But the no simpler comes in the next line, because what we do is we take the gas that we generate and we run it back to the incoming biomass, and what that does is that filters out any tars, any particulate, any moisture, things that we don't like, and we recover the heat that we put into it, and that makes the operation more efficient. And we have the same first stage for both electricity and fuel production. So we worked with a lot of different biomass materials. This is a partial list of them. We've actually tested between 50 and 60 at this point. Pretty much all of them work fairly similar. There is some difference because the energy contents will be different between them. But for the most part, you can adjust for that by adjusting the feed rate that you put it into your system. And you can tell that we've worked with materials from all over the world. From Indonesia, we got the palm kernel shells and the palm fronds. We've worked with mesquite from Australia. Pretty much, we have interest in this product and the materials pretty much over the planet. To get into the benefits of this, I'm done with the technology now. You can wake up. This is the levelized cost of electricity as a function of different feedstock materials. And the way to look at this chart is about 3.5 to 4 cents per kilowatt hour is the operation, maintenance, and write down of the equipment. The rest of it is the cost of the biomass itself. And to give you a perspective, your electrical bills in this area are probably around 10 cents a kilowatt hour. The other way to look at this is from the Energy Information Agency. Once a year in July they come out with a new report. This is for new installs going in 2018, and it's the right-hand column that's of interest because that's the sum of the levelized cost of electricity, and what we've done is we've superimposed our chip gas onto that, our chip system, and we're at $59 a megawatt hour, or divide that by 1,000 for your kilowatt hours, so 5.9 cents a kilowatt hour. The next cheapest electrical production is advanced combined cycle natural gas at $65 a megawatt hour. So we like the position that we're in from a competitive standpoint. Another way to look at the hydrogen cost is a kilogram of hydrogen has 92% of the energy content of a gallon of gasoline, and we can produce a kilogram of hydrogen for 30 to 78 cents a kilogram, depending on the cost of the feedstock itself. So think of it as less than $1 a gallon for energy equivalent. In addition to good economics, the other thing that was important to us is we have a good energy payback ratio. In other words, what we mean for the amount of energy you get out for the amount of energy you put in to make the material. And for example, we did not want to be in another corn ethanol trap where perhaps you get only 30% more energy out than you have to put in to generate the ethanol. And everything is out of the literature with the exception of the 2 green bars. And the lower green bar is an energy crop like switchgrass. And in that case, what we do is we take into account all the energy that went in, that the farmer used to plant the crop, to harvest it, to get it to the farm gate, and then the transportation to the plant, and then the chopping of the material that we have to do on our end. And there we get about a 7-to-1 energy return for energy invested. If you use a waste product like, say, sawdust, for instance, we don't count the energy that went into creating the waste. So in that case, we get a much higher return, about 11.5 to 1 energy return for energy invested. Another way to look at this is it takes about 1.5 kilowatt hours of energy in our system to make a kilogram of hydrogen. If you do it by electrolysis, which is just running electricity through water, and that technology has been around for about 150 years, if you do that, then it takes 55 kilowatt hours of electricity to generate that kilogram of hydrogen. Most hydrogen in the world is made by natural gas reforming, and when they do that, they lose 13 kilowatt hours in the process. So the economics are good, the energy efficiency is good. The other thing that was important to us was that the environmental piece be good. And you can see in this next slide, this is a study that was done for one of our customers in England by ARUP, another English firm. And this study was so independent we didn't know they were doing it. But then they shared it with us later. And what I've done is I've superimposed on there the new EPA mandate. And you can see that the new EPA mandate pretty well skewers most ways of generating electricity except for combined cycle natural gas. And that's for pretty large systems. Now we're about a factor 50 lower, 50 times lower, so we're not affected too much by this. The other thing that was important was a study done by Dr. Adam Taylor here at the University of Tennessee. And he looked at our what we call our liquid fuel or synthetic fuel. This is gasoline and diesel. And he did a complete environmental study, not just CO2 emissions. And if you notice, every category is negative. Now, in environmental work, that means reduced impact, so, negative is positive. That's a good thing. So in addition to the good environmental parts of it, we do have two co-products that we have to offer or to deal with. One of them is water. And as I said before, we get half a ton of water for every ton of biomass that we process. And we can effectively recover about a third of that. If I had a magic wand and I could replace all the energy production in the U.S. With our technology, we would actually generate 3 times as much water as the U.S. consumes. So that gives you some idea of an opportunity along with the electricity and liquid fuel. In addition, we have our product called biochar, and as I mentioned before, this recovers all the minerals that the plant took out of the ground. It has a pH between 10 and 11, so it makes a great soil supplement. Because we process it at very high temperatures, we have very low volatiles in our material. A lot of biochar that's processed at lower temperatures will have volatiles all the way up to about 70%. But in our case, you put this in the ground and it'll stay there for centuries. It's a great soil supplement and a great carbon sink from that standpoint. The other thing, some recent studies over the past 2 or 3 years that are pretty interesting is to feed it to cattle. Now, they've known for a long time, probably a century, that if a cow has stomach problems, what they do is they give it charcoal. In fact, if you have stomach problems, they'll pump your stomach and give you charcoal too. But what they found is by adding about 0.5% biochar to their feed, to the cattle feed, because their stomach now is processing more efficiently, it can reduce methane emissions by 22%, which is good from an environmental standpoint. From the farmer's standpoint, what's more important is for the same amount of feed, it puts on about 25% more weight, which also has the benefit of not consuming as much. So now, this is a very non-scientific study done by our hero, Ted Wampler. These are 3 tomato plants, and on the left you see a regular tomato plant. In the middle you see a tomato plant with biochar. And on the right you see a tomato plant with biochar plus nitrogen. Now, our biochar by itself doesn't naturally have nitrogen in it, but we think that's a great visual. So to move to the next step, I'm going to talk a little bit about Proton Power itself. We've been at this for effectively for about 5.5 years at this point. We are in early stage commercialization, but we do have some really well-heeled, very nice customers because we have almost $1 billion in signed orders. Now, I have to tell you that's a little bit misleading because the customers get to say when we actually start on those. But we do have active contracts, and we're working very hard and growing very fast. We do have 3 locations, 85,000 square feet of manufacturing and office space on 125 acres, and since we did the press release, we've added 12 employees, so we're up to 94 employees, including 20 engineers. It's a high-tech operation. We do need a lot of technical help. And I have to tell you that this is a terrific team that we're working with. And this is not a one-man show or a two-man show. This is really a team effort, and we have a great team of really smart people, and they are fun to work with. Our shop is ASME qualified, which means we can make up to and including pressure vessels if we have a need to do so. This is a picture of some of our facilities. The first one we call the farm, and that's because it was a farm. And on this farm there was a house. And that house is now our headquarters. And my wife fixed the house up, and it's a great headquarters. And behind it is our entrepreneurial garage. You know, every entrepreneur has to have his garage, and pretty soon General Electric, I guess, will have us on their ad. But it was a 3-car garage, and that's now our R&D center. In the middle is our production facility, 23,000 square feet of manufacturing and office space. And on the bottom is a 83-acre site in Rockwood, and there we plan to put up the first liquid fuel operation. The top 2 are in the Roan Regional Business and Technology Park, as is this facility, and we're supposed to close on this day after tomorrow. It's 11,000 square feet, and we're going to move our chemical lab and metallurgical lab into this facility. Just some pictures into the manufacturing operation. You can see it's a typical fabrication shop, machining and welding and shears and brakes and this kind of thing, with a great group of people working it. Now to talk a little bit about the scalability of the technology. In the upper right we have our Wampler Farm sausage, which is the half of a megawatt nameplate, but actually has a megawatt on it. And on the lower left is a 500 megawatt facility that we quoted for the Japanese. After the tsunami, the Japanese came in and they were looking for other alternatives. And we took a serious look at this and actually quoted this thing. They went away. We thought they were perhaps gone forever, but sure enough, about a month ago, now they're back. So we may end up doing maybe not something that big, although they want 1.8 gigawatts worth of new installs. Another piece of what we're doing, we have a sister company in Boulder, Colorado, that our son, also Sam Weaver, is running. And what they're doing is they're working with a Stirling engine. A Stirling engine just operates off of the temperature difference. Stirling engines have been around for about 200 years. But they have now developed the most efficient Stirling engines in history. And the sweet spot is waste heat recovery. And so what you see here, the cylinder there on the lower left, that's the Stirling engine. And what they're doing is they're taking the waste heat from generating electricity off of this generator and generating more electricity. So in effect, what you have is you have more electricity coming out for the same amount of fuel going in. So it's a highly effective way to improve the operations of your generators. Now I'm going to tell you a story about why we're different. I'm sorry, I'm going to tell you a story about how we're different. And in September last year, Carol and I went to the conference in Chicago, and it was a thermochemical conference, and there were people from all over the world that were trying to do exactly the same thing that we were trying to do, which is to make liquid fuel from biomass. And when you listen to the talks, what really struck you was that everybody was starting at the same spot, fluidized bed with the catalyst in it. They would make this, what they call fast pyrolysis oil, at about 500 degrees and then cool it down. And everybody was starting at the same spot, and everybody was stuck at the same spot. And the reason they were stuck at that same spot is because they called it, strategically, they called it bio-oil, which was a big mistake. If they call it what it really is, which is a highly acidic, oxygenated stew of about 800 molecules, they wouldn't have been so inclined to try to throw it over the fence to the refineries to get them to finish the job. For about 16 months, we were headed down a similar path, not the same path, because the other path that other people are working with, it also involved fossil fuels, because the hydrogen that they were using comes from natural gas. In our case, what we had planned to do, take one of our chip units to make the hydrogen, the other one to make the bio-oil, and then while everything was at temperature, we were going to upgrade it with the hydrotreating and hydrocracking, and then do the distillation on the cool down. And for about 16 months, we headed down that path. This is a system we built for the University of Tennessee. In fact, they were our very first customer, not commercial, but our first customer. And it was building this system for us that actually got us interested in making liquid fuel, or petroleum-like material. And sure enough, for 16 months, we worked at that, and we made what's called bio-oil. Looks like oil, doesn't it? But it's not. This has about 35% water in it, and all the molecules in there have oxygen associated with them. What you put in your gas tank doesn't have oxygen in there unless they add ethanol. It's just what we call hydrocarbons, just hydrogen and carbon in the atom, just straight hydrocarbons. And we worked through the process, and sure enough, we distilled some, and we got some diesel on the left, aviation fuel in the middle, and gasoline on the right. So it was possible to do it. But if you take a close look, those are little 2-gram bottles with a few ounces in them, taken on our conference room table. And this is an illustration of why it's so difficult. The oil that's in the ground that they pump out has been stewing in the ground for 200 million years, and all the oxygen has been forced out of it. And so when they take it out of the ground, the energy content is the same as the energy content that you're going to put in your gas tank. Now, they may change the molecules some, and they certainly have to clean it up, take out the sulfur, but they're not doing anything in terms of fundamentally changing what they get. But if you start with biomass, it's a big deal, because now you're trying to concentrate the energy by 3 times, and you're trying to take out the oxygen, you're trying to take out the moisture, and you're always fighting nature when you're doing that, and it's quite a struggle. But we had a clue that there might be a better way. Some of these clues hit us over the head, and some of them were real subtle. The final clue was a report that Cool Energy did for us in Boulder, Colorado. And they wrote a report, and they kind of had the final clue. And so Dan and I were talking about it, and Dan said, I know how to do that. So we went out to the shop, and he said, we'll modify this piece of equipment. And 2 weeks later, the day before I left to go on Christmas vacation, we now got this. That may not look like much to the first appearance, but those are all hydrocarbons, no longer oxygen in the molecules. And so all of a sudden we had the good stuff, and we're calling this our Christmas miracle, because indeed it was a Christmas miracle. to be quite frank, we were not expecting to get to the finish line in one shot. This was a complete surprise to us. It's a very different process, very different from everything else that we're doing, everything everybody else is doing, everything we were doing too. Then we distill some of it. On the right we have regular diesel distilled, and on the left we have our product distilled. So then we brought in a professor, Dr. Jeff Hodgson, used to teach mechanical engineering at UT. He's helped us with a lot of our engineering issues over the years. And we said, okay, can we blend a little of this in regular diesel and run it? And I said, maybe 1 or 2%. And he said, don't waste your time, at least do 10%. So we did 10%, 25%, 50%, and 100%. And, of course, everybody was kind of excited about this, and so they gathered around, and this was our first run. And I asked Jeff, how will we know if we had a problem? And he said, well, you'll know because the engine will start knocking. Oops. Listen to that hum. So what do we do with this? Well, what we're planning on doing is making turnkey plants where you can make 50,000 liters a day worth of diesel fuel. This is what a typical layout might look like. This sits on about 2.5 acres of land, and our first installation for this is going to be down in Rockwood. And the reason other people are interested is here, because they really like the economics. You're talking about all-in costs of about $1.78 a gallon, and if you've been to the pump lately, you know that that's not bad. I'm going to back up from a history standpoint and talk about why we're different. We just came from a different spot than other people who are doing similar things to what we're doing. As I mentioned before, Dan and I have worked together for 42 years, and we started making neutron absorbers for the large commercial nuclear power plants. And the alumina B4C burnable neutron absorbers that allowed them to go in with a higher initial fuel loading, so they could go longer before they reload. And so they could stretch those reactor cycles from 12 months to 24 months. And then we started making the control rod material actually control the power level of those multi-billion-dollar machines. And we would put about 250,000 of each of those products right in the core of the nuclear reactors. And because we made a better product, we drove 90% out of the manufacturing costs. We made a better product, and when we exited that market, we had an 87% market share on a worldwide basis. And we've had 4 major exits over the years. That product is still made today the way we developed it in 1970, and some of it's still made here in Knoxville. Along the way, we started making test and research reactor fuel. This was high enriched uranium. We bought out Gulf United Nuclear, National Lead, and Atomics International. And there for a while we were supplying all of the test and research reactor in what was considered the free world, except for 2 reactors. And about 10 million people a year would get treated with the radioisotopes from those reactors. If you've flown on a Boeing 767 or Boeing 777, you've been stopped by brakes made right here in Knoxville, carbon-carbon brakes. The new Dreamliner, 4 military aircraft, some of the Airbuses, almost all of the Formula One race cars, all that starts here in Knoxville. We made the first 2,800 degree C production furnaces for making high-strength, high-modulus carbon fibers. To give you a sense of temperature there, that's half the temperature of the surface of the sun. These production units had about 15 feet long hot zones, and we made the first one and 5 of the first 7 in the world. Then our most famous or infamous, depending on whether you like Coors beer, we helped them develop a silicon nitride punch to replace tungsten carbide. The silicon nitride has about a fourth the weight, and so they could make those beer cans about 10 to 15% faster and much thinner, and so they advertise the coldest beer because they have the thinnest beer cans. So in 2006, Dan and I gave up the beer and brakes, and well, not all the beer, but I'm going to go through a series of thermochemical processing systems that we built, and in every case, the customer just came to us with a sheet of paper, and we did all the design, the engineering, the manufacturing, the installation, and the training of the employees. This is just so you have a feel for why we're not afraid to tackle the technology that we're underway with now. This is a system that was built for manufacturing sciences in Oak Ridge, and what they would do is they would heat treat depleted uranium military tank penetrators, about 5,000 pounds at a time. It would start out with a high vacuum, go up to about 1,200 degrees centigrade or about 2,000 degrees Fahrenheit. And then there was a gas quench system, so it would quench it so they could turn this around every 24 hours. This is a system that we built for General Dynamics down in Fort Worth, Texas. This was for making carbon-carbon wing spars for military aircraft. This is about a 6-foot diameter, 6-foot tall hot zone, went to 2,200 degrees centigrade for about 4,000 degrees Fahrenheit. This is a system that we built for Saint-Gobain. They're the largest ceramic manufacturer in the world. In this case, what they were doing was they were making silicon carbide carriers for silicon wafers for the computer disk industry. And the problem was they couldn't keep from contaminating the wafers with carriers. So what we did, we built them a system that would lay down a pure layer of silicon carbide over the other silicon carbide and basically trap the impurities in. So this system used methyl trichlorosilane gas, 6 feet diameter, 10 feet tall, and the fellow down there below, Martin West, is about 6 feet 4, and that gives you a sense of scale. They actually built this into a parking lot and then built the building around it. As a result of that work, we got this work in Bexbach, Germany. This was about the time the wall fell, and there was a big demand in East Germany for sanitary ware. So what they were doing here is they were making the kiln furniture that they put the sanitary ware on to do the firing. Once again, it was silicon carbide beams that were about 15 feet long. And these beams, they would fire about 5 tons at a time. 2-day firing cycle, went to 2,600 degrees centigrade over 5,000 Fahrenheit. And that yellow device you see there, we built out here in Knoxville and flew it over. This is a look in the end of one of those furnaces. And it shows you another couple of product lines that we had. We were making a rigid carbon-carbon and soft carbon-carbon. It's also how we got started doing what we're doing now. Because when you go to these kind of temperatures, about the only thing that stands up is carbon. So we were making our own carbon fibers, and we had these reactors running around the clock with this flame shooting out. And in 2007, when Dan said, let's do something again, and we started talking about that product, then we realized we'd been throwing out the baby with the bathwater. Because hydrogen had a whole new meaning to us now. This is another system we had in our own shop for firing carbon-carbon separator plates for United Technologies for their phosphoric acid fuel cells. Some of those things ended up in the space station and the space shuttle, to give you an example. Once again, that's half the temperature of the surface of the sun, about 5,500 Fahrenheit. This system is what we built for Coors, 1,800 degrees centigrade, about 3,000 Fahrenheit, and 1,000 psi pressure. And this last one, this is one of 4 furnaces here in Knoxville, still making carbon-carbon aircraft brakes. As far as we know, this is still the only single-step processing for aircraft brakes in the world. This is a 6-foot diameter, 10-foot tall hot zone, went to 2200 degrees centigrade, about 4,000 Fahrenheit. To give you a sense of scale, that guy in there, that's the guy in there doing maintenance. So what's the point of all this? Where are we going with it? Well, I don't know how many of you have seen this, but this is a relationship of wealth to energy availability. The vertical axis is gross domestic product per capita. The horizontal axis is kilowatts per capita. And of course, there's the U.S. in the upper right-hand corner. The interesting thing about the U.S. number is it's been flat for 40 years. And it's been flat because even though we have houses that are twice the size and cars that are twice the size and all kinds of electronic gadgets, these have all been offset by increases in efficiency. So the good news from that is you can take the population of the planet and look at, okay, what's the energy demand? And, of course, one response is, well, we got it and you can't have it. That doesn't seem to be working. This is the world average down here. Of course, that includes us in it. The really important number is down here. It's the median income on the planet is $850 a year. And the reason is they don't have access to energy. So what if you were to do something about it? What would it look like? The world continuously consumes about 15 terawatts of energy. If the world had what we have with our current population, it would be 84 terawatts. And what that means is Exxon and Shell and Chevron and all of these huge companies creating this enormous amount of energy is only supplying 20% of what the world needs. So one way to think about getting there would be to add 2 terawatts a year. And if your equipment lasts 60 years, then after 60 years, then now you match the population of the planet with the energy need. My mental image of 2 terawatts a year, that's 6 large 1,000 megawatt electric nuclear plants like Watts Bar coming online every day forever. That's the magnitude of the problem. That's not likely to happen. But you can do it with biomass. And the way to think about doing it in biomass, almost all of you came here in a car that has a 100 kilowatt motor in it or more. And 20 million of those 100 kilowatt engines is your 2 terawatts. Now the world already makes 78 million, and they increased by 20 million from 2001 to 2010. Now I'm not suggesting that that's how you do it, but that's just to show you that it's not a stretch to think you can expand your production capacity to actually do that. And so what would it look like if you did that? Well, $5,000 billion worth of new installs, 50 million manufacturing jobs, 10 million new support jobs each year. We're happy to report that we think this is the biggest business opportunity in history. So how long are fossil fuels going to last? Everybody has their own opinion. Most opinions don't go much over 100 years. My mental image on this is Carol and I went to the World Energy Conference in Rome in 2007, and the Saudi oil minister stood up and said, we got plenty of oil. You Americans got to get busy, but we got enough to last 200 years. And then the same guy in 2010 in Montreal, they hold these every 3 years, same guy stood up, and I guess he thought he had a different audience because he said, we got enough oil to last 80 years. I'm sorry to report I didn't get to go this year. The other mental image I had is I just happened to catch a 60-minute program in which this reporter was interviewing this Saudi oil minister, and they were in this space-age control room in the middle of the desert, and he was explaining to her that they were importing seawater 150 miles into this, right in the middle of this desert to force the oil out of the ground. And he said, this is the largest oil field left on the planet. He says it's larger than the North Slope of Alaska, it's larger than the Gulf. He said, we have 18 billion barrels. Well, just to give you some perspective on that, that's enough to last the world 7 months. So we do have to make a transition. And you can do some with nuclear. You can't do it all, but you could do a lot with nuclear. But if you don't recycle and you don't bury, you might as well take it off the table, because it's a limited resource just like any other resource if you're not going to use 99% of the energy in the fuel. So at some point, even with nuclear, we have to move to a sustainable, renewable future. You can do a lot with wind and solar, but both of them are discontinuous. We don't get a lot of sunshine about midnight, and the wind doesn't always blow. And we're happy to be the enabling technology of other technologies. And the way we look at it is kind of the way the farmers look at it. You know, the farmers all compete with each other to supply food to the market. But they don't look at it that way, because the market is so huge that they help each other out. They don't think of it as being competition. We're the same way. We don't care how much of anybody else's technology you use. We're happy to have other success stories. We'll just pick up the 80% that they've left laying on the table. So I'm going to give you an interesting thing to think about. You know, the world has gotten into it's my way or your way or my way or the highway. And we don't think it has to be that way. It doesn't have to be either or. It can be both and. Now, the world currently produces about 88% of their energy with fossil fuel. If I get my magic wand out again, and now I want to replace the whole world energy production with ours, what would that look like? Well, because the Earth takes out about 3 ppm per year on its own, and our technology, carbon negative, if we had nothing but our technology, we would take out about 10 parts per million per year. And then after a decade, your atmosphere would be back to where we started. Now, I don't have that magic wand. Mine doesn't work anyway. And what you can do, though, is you can add new energy sources using technology like ours that's carbon negative. And by the time you've added 44% more, another 7 terawatts, then you will have technology that's carbon negative enough to offset all of the emissions from the carbon fuels. Another way to look at this. So that's our story, and we're sticking to it. And I'd really like to thank the Howard Baker Center for giving us this opportunity to tell our story. This is a great venue for the university, for the community. And Howard Baker is a special person. I had to have the opportunity to meet him on a couple of occasions. He's a really great guy, a gentleman's gentleman. And I'm honored to be speaking in his facility. Thanks to you for listening to my story without throwing tomatoes. And thanks to our great Proton Power team, because this is a team effort and we have a great dedicated team. Special thanks to Dan Hensley and Jim Bierkamp. Jim is our business development guy, and Dan is our operations guy. And a special honor to Dan for the wind beneath my wings people. Dan Hensley, my business partner, and my wife of 48 years, Carol Weaver. Thank you so much.
Take some questions from the audience?
Yeah.
Very good. Dr. Weaver has expressed interest in taking some questions from the audience, so I'll ask if we have hands. We're recording this, and so we would like the questions to go through a microphone.
You know, do you think you could revolutionize farming? And 2 inputs, and then I'll give it to you. What about small farming versus big pharma? And also, is it possible that big pharma, or farms in general in America, produce a limited number of products because they can sell so much of it, and it's mass money, and they avoid so many other fruits and vegetables? Does that make sense?
Yeah, but I'm not in the political arena.
I'm not trying to address that. I'm just saying maybe there's opportunity for many more fruits and vegetables, but farmers don't see it as economics for them. When the other arena is great nutrition.
Yeah, I think the issue really is a little different, and that is, if you go up into Iowa now, I married my wife from Iowa, and she grew up on a 400-acre farm, and my brother-in-law is still on that farm. When we used to go up there, they had maybe 300 cattle, they had maybe 1,000 pigs, they had chickens, they had a dairy herd that I helped them milk. That was a test, to see if I was good enough. But if you go up there now, you don't see many animals. And the reason is almost all of the crops up there that are being grown are energy crops. They're being grown for ethanol production and biodiesel production. And to make a distinguishing point here, our stuff is not biodiesel. Ours is a drop-in diesel. It's the same chemistry as petroleum diesel. A biodiesel that they make from soybeans, for instance, is a different chemical. But we think it is an issue, and that's why we think our technology, because we can use all kinds of waste material, we don't have to compete with the food. And we sort of showed that on that first video. We can take the part of the waste, like the corn stover and so on, that the farmer doesn't use for the corn. But even the small farmers now are doing very well, but because of the price. And you don't have, I'm sorry, but we don't have many poor farmers these days. They're in the 1%.
You mentioned that the feedstock that you use in the biomass process picks up what's in the soil. And I'm wondering if you've done any experiments with contaminated soil. Various, I could mention a few, but, and what that does to the char, and does it all appear in the char? Is it easy to collect the char and to handle the char with it being contaminated?
Yeah, thank you. The answer is we haven't done it with contaminated soils, but what we have done is take demolition and construction wood waste, which has pressure-treated wood, and we ran it through our system. We're working with a company in Raleigh, North Carolina. We ran their material through, and then we sent the biochar off to be analyzed in Nashville. And sure enough, they identified 6 toxic materials in that biochar. And then they did a leach test. And what they found was only one of those 6 was leachable, and it was 200 times lower than the EPA limits. And the reason is the biochar is we make it because it's a high-temperature biochar. It has a very high surface area. It acts like an activated carbon. And so it grabs hold of that stuff. Now, you wouldn't want to put that back in the soil with your plants. That is something that you have to put into a landfill. But at least what you're putting in the landfill is reduced by 25 times.
Yes, we know that refineries and nuclear plants have their safety issues, or potentially. On the scale of production of energy, how would this technology appear in terms of safety?
Well, we certainly we're making a flammable gas, and we're making a flammable liquid. So you have all of those safety issues that you have with dealing with those gases. In terms of, I happen to like nuclear and happen to think at least if you use a pressurized water reactor, they're really pretty safe. The only problem we've had is with the pressurized water reactor was 3 Mile Island, and that certainly wrecked the utility, but nobody got hurt. And as a matter of history, our aluminum V4C pellets were in there, and it was the only thing that survived intact in the core of that reactor. But there's no question, you know, it's like having natural gas or anything else. It is flammable gas. You do have to be careful with it.
So you have limited operational experience. How do you know, or how do you estimate the durability, which would relate to the operation and maintenance costs of your system?
Well, we have been running multiple prototypes, and when we started, we learned a long time ago, you better build big stuff, because if you build a little bench scale stuff, you're not working on the problems that you need to work on, and you are working on problems you don't need to work on with the big ones. So we started, all of our prototypes have been equivalent of, say, 100 kilowatt electric size systems. We do have 5 years of operating multiple prototypes and multiple generators and so on. So we do have some experience, but there's no question that we're going to have learning experiences as we move down the road.
Word? Got one more question, Nisa, and that will be it.
Sam, there have been some significant improvements in the efficiencies of solar and power generation and solid oxide fuel cell developments. Are there opportunities in this technology for comparable significant improvements in the efficiencies?
Well, we certainly hope so. Our Christmas miracle is 4 months old now. We're expecting a lot of improvements in efficiency, and with the electrical power generation. Now, over time, you know, they've been doing solar for, I don't know, 50, 60, 100 years, you know, so they've had a lot of time and a lot of money to cram down the cost. And we're all for that. You know, some of the problems are really just fundamental, unlike solar, and that is that the sun doesn't shine at night, and there's not much you can do about that. And so, fundamentally, they get the equivalent of 6 full hours a day. 4 full hours a day equivalent. So you have to divide theirs by 6 or multiply their cost by 6 to get an equivalent. I think somebody had a question over here.
I had a question about the water recovery, and certainly water pressures are very much in the news. So when you're counting the water that you're recovering, is that for a dry ton on a bone dry basis, or is that including the moisture in the biomass?
No, that's on a bone dry basis.
Okay.
If you have extra water, that's a bonus.
Sure.
Called for final word a moment ago. I got 2 questions. I'll try it again. Any final word? Okay, it worked.
You had listed on your paper if your business has a large source of biomass. What do you consider a large source of biomass?
Well, it takes 20 tons a day worth of biomass to run a megawatt of electricity on a continuous basis. To give you a sense of perspective, and for a 50,000 liter a day plant, or 4.8 million gallons a year, we're looking at about 50,000 tons a year.
Additionally, the video that you showed, was the unit running on, you said you tested at 10%, 25%, 50, and 100. What was that video? Was that 100% or? No,
that one was actually 10%.
Okay.
And I've got one that's 100% if you want to come up afterwards. It doesn't sound any different. The other one didn't have any people around. It was just a machine. I thought this was a little more interesting.
Okay, Dr. Weaver, I want to thank you for coming, sharing your story, the technology. The best of luck to you, because the luckier you are in this, I think the luckier all of we are in the room and around the world. So thank you very much for coming.
Thank you very much.